Here we have a unit circle. You'll remember back in the days of trig, we spent a lot of time looking at this unit circle. And in particular, it was in studying this unit circle that we were first introduced to describing curves parametrically. Remember, instead of talking about this circle being x squared plus y squared equals 1, we said, well, let x be cosine theta and let y be sine theta. And that's the way we could describe points on this circle. And in fact, I've done that here, except I'm using K, so I can use the slider down here on Desmos. But notice that I can start this circle, start the K going, running through the angles from 0 to 2 pi. And notice it shows little motion around the circle. Think about this. Think about if this were um, maybe a particle moving in this motion. So a particle starts over here at 0 or at 1, 0, and it just starts moving around the circle like this. Now you notice we talk about this particle moving around the circle as one thing. But you know what's going on here is there is a horizontal component here and a vertical component. Let me show you what I'm talking about. Let me fix, taking this cosine k, sine k, let me just fix the vertical component at 0 and see what's going on horizontally. And here we have it. So let me start this k back at 0. Now notice this horizontal component right here, the x part, notice what's happening. It's simply giving you the x value. So if you look at this, so this point right here, it has an x and a y value. The x value is right here. Okay, that's the x value. And as this thing moves around, all this does is represent what the x is. Okay, that's what that is. Now let me throw in the vertical. Okay, so here we go. Now here's the vertical. Notice now it's just tracking the vertical coordinates. Okay, so if you look at the y component here, this represents the y component. Now, so it looks like what we have is we have kind of three functions involved here. We or we have three different things that we're looking at. We're looking at the vertical component here, which is its own function. That's sine theta, in this case sine k. We have the horizontal, which is cosine, right? So there's two distinct functions there. And what these two functions are doing, one is giving this the x coordinates and one is giving us the y coordinates of the circle. And up here, the cosine theta, sine theta, cosine k, sine k, that's bringing those together. This is like a package of functions here. You've got the horizontal component, you've got the vertical component, and then we put them here in a nice package that puts them together that gives you a position of the particle on the circle. So here's what we have. We have the cosine. We have the cosine t, let me use t now, and sine t. And this describes a unit circle. And in particular, let's think about x of t being the x component, cosine t, and the y sub t, or not sub, y of t equal the vertical component. Okay, so we have these two functions. Now we can talk about this. We can talk about dx dt. We can talk about the change in the horizontal component with respect to t. So this would be negative sine t. That's the derivative of cosine, negative sine. And we can talk about dy dt, and that would be cosine t. So we can talk about the change in the horizontal with respect to t, and we can talk about the change in the vertical distance with respect to t. But what happens if I want to find dy dx? In other words, let's suppose I want to find the slope of the tangent on the circle. Well, I'm not going to get that from this one or this one. So what we want to do is figure out, well, is there a technique if I have parametrically defined uh, curve, how can I find the slope of the tangent? In other words, dy dx, which is different from dy dt, different from dx dt. So let's look and see how we would do that. And I want to get away from the unit circle here a minute and just talk about curves in general. So let's suppose we have a curve here, and let's suppose that this curve is defined, it has an x component, whoops, an x component and a y component. And this curve is parametrically defined, x of t, y sub t of t. Okay. Now, let's suppose I want to find the slope of a tangent at this point right here. Okay. In other words, I want to find the slope of this line right here. Let's suppose that's a tangent. In other words, I want to find dy dx. Well, remember the approach that we took when we first started talking about derivatives. We said, okay, well, let's think about the slope of a secant. So let me just make a secant. It's not the tangent, but we'll just use it to kind of approximate the steepness of the tangent. So down here, I have this point, x of t, y, I keep saying sub, I think, x of t, y of t. And then up here, we have another point, which is going to be x of t plus delta t. Okay, that's that. And this is y of t plus delta t. Okay, so we have this other point right here. Now, you can kind of remember back when we first started talking about the derivative and how we approach that, defining the derivative. What I want to do is I want to get the slope of this line right here, this red line. And you know that that would be the change in the y's. Okay, and here's the one y minus the other. The change in the y's over the change in the t's. Okay, so this is x of t plus delta t minus x of t. Okay, that's the change of the y's over the change in the t's, and that is the definition of slope. Now, I want to do something a step further. I'm going to divide the top and the bottom by delta t. I'm going to multiply the top and the bottom by 1 over delta t. That's just like multiplying by 1. So that doesn't hurt anything. So I've got y of t plus delta t up top minus y of t. And then right underneath it, I've got delta t. And I do the same thing to the bottom. I've got x of t plus delta t minus x of t over delta t. Okay, there I have it, the top and the bottom. Now, here's what I want to do. I want to take the limit of this whole thing right here, as delta t goes to 0. So let's do this. Now I'm going to do it this way. I'm going to do the limit of the top over the limit of the bottom. So the limit as delta t goes to 0 of y of t plus delta t minus y of t over delta t. This is what's up top. So I'm doing a limit of the top over a limit of the bottom. That's the way I'm taking the limit of the whole thing. And then down here, the limit as delta t goes to 0, same thing, of x of t plus delta t minus x of t over delta t. Now, if you just take a moment to dig what this top is by definition, the definition of a derivative. This is the derivative of y with respect to t. So this top thing is dy dt. That's what it is. Likewise, the bottom is dx dt. So it's the derivative of the y with respect to t over the derivative of x with respect to t. And this right here is dy dx, dy dx. In other words, it's the slope of this line right here. We're just going back to early days in Cal 1 when we defined the derivative. And we're saying, well, take this secant line and let the difference between the 2 points go to 0 and you get the tangent. So we get the slope of the tangent, which is dy dx. This is what we found. So we know now if we have a set of parametric equations, how do we find the slope of the tangent? Well, we take the change, we take the dy dt, that goes up top, over dx dt. So let's look at an example. Let's suppose that we've got a set of parametric equations. Let's say x is equal to, let's suppose we've got t squared and y is equal to t to the fourth, let's say. So we've got these parametric equations defining a curve. Now, what we want to do is we want to find the slope of the tangent, dy dx. So I take the derivative of the y part, see? This one right here, dy dt, which is going to be 4t cubed. See, that's just the power rule. Over dx dt, which is 2t. Now let's see what we've got here. We've got 2t squared. Yeah, so there is our derivative. That's dy dx. Now notice, let's just think about what if we eliminated the parameter up here and then we found dy dx? Let's see what that would look like. Well, t squared is equal to x. So let me do this. Let me just say that means that x squared is equal to t to the fourth. T to the fourth. I just squared both sides here. That means down here I have y equals, in place of t to the fourth, I'll put x squared. Now let's differentiate it. dy dx is equal to 2x. There. Now notice x is equal to t squared. So this and this turn out to be the same. So we found dy dx. Now that's all you have to do. You're not using the quotient rule, anything like that. You're just taking the derivative of the y component with respect to t over the derivative of the x component with respect to t.